streaming. Okay, so I did add a little bit more stuff, onto Canvas. So remember I said, the things will be streaming in as I start to write more stuff. So we got basic quantifiers added in. I don't think we talked about that yet. Okay. There's also set theory using quantifiers, basically to re-explain, set theory, or at least the notations in set theory, but this time using quantifiers. And there's also a homework assignment, which is this one. Your basic set concepts is a homework assignment. It's due next Monday. You have 1 week to work on it. And functions, I'm still in the process of writing about functions. It's partially done. I haven't really put a link up there yet, but that's okay because I think, today we'll be talking about, we'll be finishing up, set theory, but we'll also start to talk about quantifiers. Okay. So let me click on the homework assignment first, just so that you know what type of homework assignment you're expected to finish in a week. I don't think you guys will need a whole week to do this. Okay, so let's take a look. So the homework assignment is just to use the web-based editor in Canvas, which is just like any other web-based HTML editors. So I want you to find out how you can define x as a set, y as a set, so that the intersection of x and y is the one single element of A. The union of the two sets would be A, B, C, D as the elements. I don't want x to be a subset of y, and I want y to be a subset of z, and z can be whatever. Okay, it just has to be a superset of y. Yep.
I just want to make sure I have it right. So if two sets are in union, they have all the same sets?
We'll talk about that.
Okay.
So that's something that we'll talk about today is to talk about what is the intersection, what is the union, how do we know one is a subset of the other one, what is a subset, what is a proper subset. So we'll talk about all those things today. So I do want to show you the homework assignment first, just so that you can keep that in mind as we go through the topics of today. Are there any questions so far about this? No? Yep, go ahead.
Our homework is online.
Yes, homework is online. It is on Canvas.
No, to be turned in online.
Yes, it is also supposed to be turned in online. You're going to use the web-based editor in Canvas to do it. So when you click on the homework assignment, I imagine there will be an area where you can click and you can do your editing inside. Okay. All right. So let's go ahead and go back and look at those concepts. So those concepts are all in basic set theory, which I think we started already. Is that right? Okay. So last week we started on the discussion of notations in set theory. We talked about how to make sure that two sets are exactly the same. We also talked about how you can have a set as an element of another set. Remember that? I gave you guys a few examples last week. We talked about how to describe a set that has an infinite number of elements. In other words, you can describe the properties of the elements instead of just trying to list out everything. The notation that we talked about last time was something like this. In order to express what is the set of all the even numbers, we can use this notation. And the notation basically says, okay, so if you scroll down, you will see an explanation of that notation. So the notation basically says, for each element in the set E, it has to meet these requirements. So the first requirement is it has to be an element of Z, but this funny looking Z represents the set of all integers. And then this symbol means conjunction or and. And then the second criterion to meet is x mod 2 has to be a 0, which basically means the number is a multiple of 2. So if a number is an integer and it is a multiple of 2, it is an even number, and then it belongs to the set E. Or it belongs to this particular set, which is set E. So are there any questions about this stuff? Because we talked about this last Wednesday. Is that okay so far? Okay, good. So in general, the notation of this is really the same thing as this. So let me just explain that one more time. P is what we call a predicate, and from your programming perspective, you can look at P as a function that returns just a Boolean. Okay, it returns either true or false, and X is a parameter to that function. So what it really means is the following. It really means X is an element of E, the set E, if and only if P of X is true. Now, typically, we don't say P, in Px equals to true, because when you just mention the predicate itself, it is implied that you want it to be true.
We would say not P if we wanted it to be false, right?
Sorry?
We'd say not P if we wanted it to be false.
That is correct. If you want to negate it, then you say not P, not P of X. Okay. So that's just a notation. But with this notation, we can describe, a set with an infinite number of elements. A set with no elements, which is also called the empty set. There are different notations, but I choose to use this notation in this class because I think it's the most intuitive notation. The other notation is a circle with a stroke, through the circle, but that is not as intuitive as just open brace and close brace, because that's pretty clear that we're describing a set and there's nothing in it. Any questions up to this point? Because this is mostly a recap of what we talked about last week already. Questions? It's all good? All right, so starting now, we're going to talk about operators that work on sets. Now, we talked about some already. We talked about the element of, but element of by itself is not, it doesn't work on two different sets. These guys do. So the first operator is called the intersection, and it looks like this. So A intersecting with B, A being a set, B being a set. When you talk about the intersection, we can describe the elements in the intersection using this notation. So you can look at this and go like, okay, what qualifies to be an element in the intersection of A and B? Well, for each element in the intersection, that element has to be in A, and that element has to be in B. So we are looking at elements that are common between the two sets. The intersection are the common elements between two sets. Is that okay? So what if I want to find the intersection with an empty set? So given a particular set X, and I say, what is the intersection of X? Not knowing what is in X, what is the intersection of X and the empty set? Can I answer that question readily? And what would be the intersection? It'll be the empty set. Very good. Because the empty set contains no elements. Okay, very good. And what about a set intersecting with itself? What would be the result of A intersecting with A? It'll be A itself. Very good. Good job. Okay. So just a reminder of what this notation means. It really means that E is an element of A intersect with B, if and only if E is in A and E is in B. If one of these two is an empty set, then one of the parts of the conjunction is not possible because an empty set has no elements. Yes?
I don't understand when you say what's the result of the intersection.
The result of the intersection.
Did you just say that? Like what's the result of A intersecting with A?
So if E is in both A and B, then it's an intersection between A and B. If it's two different things, then it wouldn't be contained. It wouldn't come
I
out.
understand that. That's knowing about the result.
It's kind of like, when you're adding, it's an operation. So intersection can be seen as an operation. So you can say, okay, what is X plus B? A plus B in normal arithmetic is an operation, so it has a result. So you can look at intersection the same way. You're given a set A, you're given a set B, and here's an operation that's called intersecting. So what is the result of A intersecting with B? So that's what I meant when I used the word result of.
Okay.
Yep.
How do you know the difference between an operation and a statement?
A statement is something that has a value of either true or false. So element of is a statement because, is this an element of that? Okay, because then the answer is either true, yes it is, or no it is not an element of. So it becomes a statement or condition. In the case of intersection, it is not returning a Boolean result. It is not telling you it is either true or false. It's just saying that, oh, here is the set of all the common elements between these two sets. So that's why it is not a statement. It is just an operation that gives you another set, a third set potentially, as the result. Is that part okay? Okay. So now, if you go back to the homework assignment just want you to create two sets, X and Y, where the intersection is a set of a single element that contains A. How many ways can we do this? Many, many, many ways. Okay? So now we look at union. Now, if you look at the definition of union, which is this one here, and you look at the definition of intersection, which is this one here, you can see that they are almost exactly the same. In fact, all you have to do is to look at the operators with a viewer. Right? If you look at the differences, the union operator is the upside down image of an intersection. And then we have this symbol here, which stands for conjunction or and it is also flipped upside down to become the or symbol. That's the only change. Okay, this is the only change you have to do in order to understand what is a union. So when you look at the union of two particular sets, A and B, okay, there's set A and there's also set B. The union would be basically elements in at least one of the two sets. Now this is, I had to pause a little bit because I have to think about, is it either or is it just at least one of them? And the answer is at least one of them. In other words, a particular element can be in A, can also be in B. That element is going to be in a union, just like a element that is in at least one of the two sets. Is that part understood? So far so good? Okay. All right. So after this, I can talk about examples a little bit. But we'll go ahead and finish up, the next operation, and then we'll go take a look at some examples. A minus B is the difference between A and B. Yep.
I'm sorry, I'm a little confused now. The difference between the union and the intersection. So you said with the intersection, there's at least one point that when you say intersect, that means they have the same points in each set.
So the intersection is a set itself. It would be a set of all the elements that are common to both A and B in our example. When you talk about union, that will be elements that are found in at least one of A or B.
So it could even include like subsets and stuff like that? Like sets inside the sets? Or I'm not sure.
No, it would be a set of elements, and those elements can be found in at least one of A or B.
Okay. Okay.
Okay, I'll give you some examples later on. Okay, and then we have minus, but minus really means difference. So A minus B would be described like this. So let's take a look at this statement here, or let's take a look at this statement and say, okay, but what does it mean? Okay, so every element in the difference E has to be found in A, but not found in B. That becomes the difference between A and B. So A minus B is a set. It contains all the elements that are in A, but not in B. Okay, is that okay? So with all of these definitions, yes, go ahead.
What if A minus B has something that's not in A?
Okay.
Okay, no, and then we try to do A minus B.
So A minus B only needs to list all the elements that are in A but not in B.
Yeah, what if there's an element in B that's not in A?
Then it would not appear in the difference.
Oh, okay, even if it's got elements that are in the set A, okay.
Because in order for an element to be in the difference or in A minus B, it has to be in A. So if you have an element that is in B but not in A, it wouldn't appear in A minus B. It would appear in B minus A, but not A minus
You
B.
can still perform the operation. Okay.
Yep.
It might be helpful to draw two circles that intersect on the board. And show,
It's called the Venn diagram.
Yeah, exactly.
Yep. But I'll give you guys some examples too. Just using text. Okay. I was too lazy to redraw the pictures. I had those pictures in the original Moodle notes, but since I have to redo all my notes, for Canvas, I have not gotten the time to redraw or reintegrate those pictures. But that's okay. I can give you guys examples using text. Mouse pad. There we go. And then we can draw some pictures using my Documents camera. It just takes a little bit of time to set it up, that's all. Okay. USB.
You said the differences is set, right?
Hmm?
You said the differences is set, but it's not. It's in A but not in B.
Yes, A minus B are the things that are in A but not in B.
Okay.
Okay, so I'm going to give you an example in text first, and then then I'll set up the document camera to look at some pictures. So let's say uppercase T would be a set of cars that I like. Okay, so I'm going to put some cars in here, MX2, MR2, MX5, and Civic Type R. Is it the Type R? Yeah. So I'll just use TR here for Type R. And I'll put one more item here. Okay, I know this is... Did I spell it right?
Yeah.
Odyssey? Doesn't look right to me. Huh?
More D.
E. Between the S and Y.
Odyssey.
No, that doesn't look right.
ODY.
Alright, find out. See, Google can...
Yeah, Y.
So it's ODYSSEY.
That's how you remember.
ODYSSEY. That's it. Okay. All right. So, and then we'll have another set, of cars that George likes. Okay. So George has a 750 BMW. He has an Odyssey and Mercedes ML. There we go. There we go. I think he likes my MX-5 too, but he would never admit to it. Okay, so now we have two sets. Okay, so each one has 4 elements. So we'll go take a look at the intersection first. I can't really use the intersection symbol here because it's not a common symbol that I can type out. So I'll just say intersects. Okay, intersects G. So it's going to be a set of elements that are found that are common in both of these sets. So in this case, it's going to be Odyssey and MX5. Exactly. What about the union? The union will consist of elements that are found that can be found in at least one of these two sets. Okay. So what do you think it's going to be? So I'm going to be very lazy. I can do this, with an editor, but not using the whiteboard, right? So, and what else should I add to it?
750.
The 750 and the ML. There we go. Let's do a minus. Okay, so T minus G would be the cars that I like, but not something that George likes. Okay, so I like the MR2, but George doesn't like it, and also the Civic. civic type R. Yep. There are really funny images about cars, you know, so they have people who put emblems of type R onto a Corolla. That's like, yes.
Makes it go faster. The sticker makes it go faster.
And the wings too.
Yep.
Yeah, don't forget the wings.
Yeah.
The wings, the spoilers, you know, they all make the car go a little bit faster. In a free fall.
No exam.
Yep.
So, and the difference of tag minus George, it's only what's in that you like that it's not that George doesn't like, basically.
Yeah. So T minus G in this case would be the elements in T but not in G.
Oh, okay.
Yep.
Want to do G minus?
Well, let's find out what is G minus T. So G minus T would be things in the set G but not in the set T. So in that case, it will be all the expensive cars, right? Really expensive cars, like 750 and the ML. So are there any questions about, you know, these particular operations? Okay, it's all good so far? Okay. So let me set up my document camera. It's plugged in already. It's got, did I plug in? I did. Because I can show you how to represent intersections and unions and whatnot, but doing it in a graphical way. So, well, let's make one more example here. Let's say A represents all the cars that Amy likes, okay? So we'll say MDX. Well, that's fine, okay? One element is okay. Okay, so in this case, you know, what would be T intersects A? What would be, you know, the elements that are common in T and A? There's nothing. It's an empty set. Sorry? Go ahead.
I said the brackets.
The brackets, okay, the braces.
Right.
These are the brackets. So
Yeah.
those are the braces. Okay.
Yep.
So T union A is going to be, everything's going to be a long list, right? MX5, Civic, Type R, all this C, and the MDX. Okay?
Yeah.
Is that okay? All right. What about A minus T? Just the MDX, which is exactly the same thing as A itself, right? A itself only has MDX, but A minus T is also just, you know, just a set with MDX. Very good. So let me see if I can fire up my document camera so they can show you, you know, graphically how to visualize all this stuff. So, yep. Okay, so it finds it. Very good. The wire is in the way. Oops. All right.
We'll just hang on the edge.
Hmm?
Is that okay? Hang on the edge. You don't want me to wrap it around?
Yeah, it's too heavy. That's why it tipped it.
Oh, okay.
So I just need the heavy stuff to be here. But lighting is awful, you know, in this particular classroom. In the other classroom, Mr. Fox, Professor Fox, you know, requested a light right at the table, so it has, you know, that light. This room is kind of really bad for this. And I can move my mic a little bit over there. Okay, that's good enough. And okay, so if you want to look at a set, okay, that's not working very well. So let's see if this works better. There we go. So if you look at this as a set, so let's call this A, and we'll look at another set, let's call this B. Okay. You can also kind of do it, you know, you can color this, or, you know, just use this to represent everything in A, and then use this to represent everything that's in B. Okay? So A intersect B would be only this portion. So if you look at how we draw that stuff, it will be the cross hatches. Is that okay? So when you want to look at A union with B, it's going to be everything inside this portion. So everything that is shaded is in A union B. Is that okay? What about A minus B?
Everything but an A, but that's not the crosshatch section.
And what does it look like?
It looks just like the lines from this way.
It looks like an eclipse, right? Yep. So it will only consist with stuff that has these lines. Oops, sorry. Let me move it up a little bit. There we go. So is that okay? So this is a kind of more visual way to take a look at these set operations. Are there any questions at this point before we start to talk about the concept of a subset? Yep.
So on the other example where we had A is the set with MDX in it, with the difference operator.
Right.
The difference operator returns
nothing. It's the difference operator will return the original set itself.
But you also said which is A. So if you return the set itself.
Okay, so in that particular situation, we have the cars that Amy like being this set here, and then the cars that I like is a set that looks like that. These two do not have any intersections. So when you are looking for the subtraction or the difference, that will be all the elements in A but not in T, A minus T. So that would just be everything in A because there's nothing in common between
Can you
these
just
two.
say A instead of listing out all the elements?
You can just say A too, yeah, because if you list up all the elements, then you get the same thing, which is just MDX in this case, correct. All right, so are there any questions about the use of a diagram to display these various operations? I can almost guarantee you that I will not ask questions that will require a graphical answer. So this is really only for you to understand the concepts a little bit more visually, because some people are more visual, so this is a more visual way to look at these operations. Okay, any questions? Okay. If there are no questions, we'll move on to the concept of subsets. Oh, we have one more first. Okay, we have the concept of a Cartesian product. So at this point, Cartesian products do not seem to be very useful, but we'll go ahead and talk about it anyway. So a Cartesian product does not give you simple elements anymore. Each element of a Cartesian product is what we call a two-tuple. Okay, so when you look at a two-tuple, okay, the term two-tuple refers to something that has two items in it. But you can see that I'm using parentheses and not braces to enclose this thing. So it is not a set, it is called a tuple. The closest thing that you have encountered already that resembles a tuple is an array. So when you look at an array in any type of programming languages, it's kind of like a tuple. So this is an array of two elements. So the first thing you want to ask is, can I have 1 and 1 in an array? Can elements of an array have exactly the same value? Yes, they can, okay? But you cannot do that with a set, okay? You cannot have 1, 1 listed at two elements in the same set because elements in a set need to be distinct or unique. But in the case of a tuple, they can be the same. The next question is, if I have a tuple, if I have a two-tuple, which is 1, 2 in parentheses, and then another two-tuple, which is 2, 1 in parentheses, are they considered the same? The answer is no, they are not the same, okay? So in order for two tuples to be considered the same, the first element have to be the same, the second element has to be the same. So ordering is important within a tuple. Is that okay so far? Okay. So then we can take a look at this operator and go like, okay, so what exactly is in A Cartesian product with B? What is the Cartesian product of A and B? Each element of this operation is a two-tuple. It consists of two items inside the parentheses where ordering is important. The first item, which is x, has to be something that is found in A. The second item, which is y, has to be found in B. Then the two-tuple xy is an element of the product of the Cartesian products of A and B. It's a cross product, basically. Okay. So we'll take a look at one example and see how we can create a Cartesian product. So we'll go ahead and take a look at, let's see, it's really great for looking at possibilities. Okay, so we'll take a look at cisp310, cisp440 as the classes, and then we'll use the multiplication symbol to represent the Cartesian product with time slot. Okay, so AM versus PM. Okay, so now how many elements do you expect in the Cartesian product? That's the first thing I want you to kind of think about is, I have two things on one side, two things on the other side, and then this is a cross product. So how many items or how many elements am I expecting in the Cartesian product? 4. It'll be 4, exactly. It'll be the number of elements in the first set times the number of elements in the second set. Okay. So what exactly are those 4 elements? So each one is a two-tuple. CISP310 offered in the morning, right? CISP310 offered in the evening. CISP440 offered in the morning, and CISP440 offered in the evening. That would become the Cartesian product of these two particular sets. Are there any questions about the concept of a Cartesian product? Questions? Now you probably have encountered this concept already. It's just that it's never called the Cartesian product. If you look at numbers on one single axis as one set, and the numbers or the values on the y-axis as another set, then the Cartesian product will span a space. It will span a 2D space. So that's one way to look at it. Okay. So I'm going to draw that picture just so that it is recorded. So when you look at a number line, okay, this is a number line. It can be integers, can be real numbers. It doesn't really matter, when we're talking about this. So you can say, okay, this is 0, this is 1, this is -1, and so on. It's a number line, okay? So it has elements. But then you can look at another axis, which also has 1, -1, and so on. So each line itself represents a set, okay? But when you look at the space spanned by these two axes, which is the 2D space, it is the Cartesian product. Because every point within the 2D space, like let's take this into consideration. So let's take a look at this point in the 2D space. It has two components. One component is a 2, which is the x value. The other component is the 1, which is the y value. It's an element of the Cartesian product. So are we doing okay so far with the concept of a Cartesian product? So at this point, it doesn't seem to be very useful, but later on when we start to talk about functions, this becomes really, really important. Yes?
Wouldn't it be 2, 1, and 1, 2?
It'll be 2, 1 only because it is order dependent. So if we always want to list the x value first, it is only 2, 1.
Is this the same as cross product?
If you cross them, yeah, then you get both.
Yeah, but 1, 2 will represent another point because 1, 2 is going to represent this point here. So they're distinct. They're not representing the same thing.
But there's no way you could do what you just did without getting both of them. There's no way you could do the cross without getting both points.
Yes, the cross product would include both points,
Yeah.
but they're distinct points. They're not considered the same. Are we still doing okay so far? Okay, all right. So let's go back to the notes here. All right, so now we have, these operators. They return a Boolean value. So the first one is called a subset of. So this is called, A is a subset of B. It is a condition. It is a statement, okay? Is it true that A is a subset of B, or is it not true that A is a subset of B? It's a question, and it has a value of either true or false. So this is true, okay? A is a subset of B is true if and only if this part is true. So yeah, go ahead.
Does that mean if the sets are equal, it's also can be that one is a subset of the other?
Yes. So in this case, the difference has to be an empty set. So if you can find nothing that is in A but not in B, then A is a subset of B. Is that okay or not?
Yeah.
Sort of.
Would B be a subset of B? Would B be a subset of B?
B is always a subset of B.
Okay.
Because when you have any set minus itself, it is always an empty set.
Yeah.
Because because you'll be asking the question, what is in this particular set, but also not in the very same set.
Yeah.
And there's no element that can be both in and not in a set.
Okay.
So that is a good observation. Any set is a subset of itself. Okay. That's good. Any other questions? But in this case, can we have some elements in B that is not in A and still have A being a subset of B?
Yeah.
Yep. Because if we're only saying that everything in A has to be found in B, that's basically what it's saying. But B can contain additional elements. It's fine. Is that okay so far?
Let's see.
So right here, I basically said, you can see, every set is always a subset of itself, because the difference of A and A is going to be an empty set of any set, okay? So now we also want to define what is a proper subset, and you can see that the symbol of a subset of has a little bar under it, and then the other one, which is a proper subset, does not have a bar under it. So this is the difference between less than or equal to as opposed to less than. Okay, less than or equal to is analogous to subset of. Less than or less than itself without the equal to is a proper subset of. So in the case of a proper subset of, A is a proper subset of B if and only if, okay, once again we are reusing this symbol here to say that A first has to be a subset of B. But there's one more thing. We also want to make sure that there is something in B that is not found in A. So B has to be bigger. It has to contain elements that A does not have. Are we still doing okay so far? Now, would this work with sets that have an infinite number of elements? So let's say we are talking about the set of all integers and the set of all the even numbers. Can we say one is a proper subset of the other?
Yes.
Yes, we can. And how do we say which one is a proper subset of which one, given these two?
Evens are a subset of all the real or all the integers.
All the integers, exactly. Yep, because everything that you can find in a set of even numbers, they can also be found in the set of all the integers.
So you can say that the set of all integers is a subset of all reals.
Say that one more time.
So the set of all integers is a subset of all reals.
That is correct.
And the real subset of the complex. Why?
Not sure whether you can claim that.
Well,
because complex number is
it's B0, why not?
Because because can you compare a complex number with a real number? That's the first thing I want to ask. can you say this real number is the same as that complex number? I'm not sure I don't think that you can compare a real number with a complex number, because a complex number has there are two components, right?
Yeah.
So which one are you comparing to when you have a single number?
Well, the b would be 0, so you just have a, you have a real number.
I don't know whether you can make that assumption.
Okay.
Yeah.
Okay.
So when you look at the set of all complex numbers and when you look at the set of all real numbers, you can say, R, Cartesian product with R is the complex number. It spans, all the complex numbers, but they're not comparable. A complex number cannot be compared to a single real number.
Okay.
At least in this class it cannot. Maybe in the math class you can make the assumption that the imaginary part is a 0 for comparison, but not in this class. Okay. All right. So are there any questions about the concept of subset versus proper subset? Okay, it's the same kind of difference between less than or equal to versus just less than. Okay. All right, so we have one last set operation to talk about. This one turns out to be the easiest. Okay, this one actually just talks about the number of elements in a set. It is called the cardinality of X. The symbol of cardinality is really just having bars on both sides. So the bar X bar is called the cardinality of X, which is a fancy way of saying how many elements are in X. Are we doing okay so far with this? Okay. What about a set with an infinite number of elements? What is going to be bar the set of all integers bar? Okay, so how do you compare that to the cardinality of all the real numbers? Can they even be compared?
Well, some infinites are smaller than others. Some infinites are smaller than others, some are bigger than others.
But they are both infinity, right? They both have an infinite number of elements. How do you compare? Okay, let me give you another example. What about the set of all the even numbers and the set of all the odd numbers? How do they compare? They're both infinite, right? As it turns out, they are considered the same. When you look at the cardinality of all the even numbers, and when you look at the cardinality of all the odd numbers, and the cardinality of all integers, and the cardinality of all natural numbers, they are all considered the same. You can actually establish equality between these things. But they are not, okay? None of these cardinalities is the same as the cardinality of all the real numbers. Hold on a second here. So you're telling me that we can compare infinity with infinity, but not with n infinity. Well, as it turns out, which we'll see later on, there are different kinds of infinities when we talk about the cardinality of a set. Okay? It has to do with functions. So we can't really talk about those concepts until we are done with the discussion of functions. All right, so with the homework assignment, are we feeling comfortable that we can get the homework assignment done?
Yeah.
In 7 days? So most of you will procrastinate for 6 days, 23 hours, and 59 minutes, and then just get it done in the last minute. Go, yep, I'm done. Yep, go ahead.
So it's due done, I guess by midnight next Monday?
No, it's right before class. Yep, so it's really kind of important to see when it is due. So when you look at the homework assignments, in all my classes, not just this one. So when you look at the homework assignment, I think this is not a student view, but I think with a student view, it will also tell you when it is due. It is due like right before this class starts, because I don't want people to miss the class because they are trying to get the homework assignment done. Is that okay? All right. So I think most of you can get started with this homework assignment already. If you have any questions about what these things actually mean, what the constraints are telling you, you can come to my office hour and we can talk about it. Okay. But other than that, we're going to move on with our notes. So let me go back to modules, and we will start to talk about quantifiers or basic quantifiers. Now, quantifiers is what allows us to specify, are we talking about there exists at least one, or are we talking about every, okay? I think we kind of started this discussion a little bit already, but we didn't really go too far into it. So the question is, if I say all professors pretend to know what they're doing, as opposed to there's at least one professor pretending to know what he or she is doing, okay? Are those two statements the same? Not the same. But each one has its own importance, okay? When I say all even numbers are multiples of 2, it means give me an even number, any even number, and I can show you that it is divisible by 2. It's a multiple of 2, right? On the other hand, if I say, I'm trying to come up with an example for the other one, which is there exists. Okay. If I say there exists a even number that is 0, okay, there's no quantity specified, then I'm only saying that at least one, you can find me at least one even number that has a value of 0. Doesn't mean all even numbers are zeros, it simply means that at least one of them is a 0. Is that okay? I cannot say that about odd numbers. I can say neither about odd numbers. Okay, let me give you these two statements with odd numbers. If I say all odd numbers are divisible by 2, that is obviously false. If I say there exists at least one odd number that is divisible by 2, that is false as well. Because there exists no odd number that is divisible by 2. Okay?
I was thinking about your whole even numbers are all divisible by 2. What about 0?
0 is divisible by 2.
But we remainder 0, so wouldn't that?
0 is an even number.
It is an even number?
Yep.
Okay.
Yep.
Is it also odd?
It is not odd. 0 is not considered an odd number. Yep.
So is 0 a number or an absence of a number?
0 is a number. It represents the quantity of 0.
It's absence.
But it is not the absence of a number. It's the absence of a value or the value of 0. Okay. All right. So we're going to kind of get into this thing here, and we'll start to look at some notations. So we'll look at this notation here, and basically, the inverted A means for all. Okay, so look at that symbol, and then every time you see that symbol, you just say, okay, for all. So in this case, it's basically saying for all x, P of x is true. That's what the statement is saying. Now, is this statement itself true? It can be true, it can be false. Is that okay? But we have one more question first, okay? Where are we getting these x from? Okay, in this case, when we say for all x, P of x is true, what are we talking about? Are we talking about professors? Are we talking about even numbers? Are we talking about integers, complex numbers, or what?
All of it.
Everything in the universe. Okay, so unless you qualify for all x applies to everything. So it's pretty hard to make a statement like this true because you don't even know whether you're talking about cars, numbers, people, historical people, fictional people, and so on and so forth. Okay. This one here is read as there exists. So this one basically says there exists at least one thing in the entire universe such that P of x is true. There only needs to be one, okay, in order to make there exists true. Is that okay so far? All right. So now we start to look into the negation of this kind of thing. Okay, so we look at the negation that is outside of the there exist, which basically says there does not exist anything that P of x is true. Okay, let me say that one more time. It is not true that there exists at least one thing x such that P of x is true. Is So now I ask you, can we say that in a slightly different way? Can we say that for everything x, it is not true that p of x is true or p of x is false? Are these two statements the same? Conceptually, just kind of think about this a little bit, okay? It is not true that there is at least one thing x such that p of x is true, as opposed to for everything that you can find in the universe, and we call it x, for each item x, p of x is false. Are these two saying exactly the same thing? Now, if you say they're not saying the same thing, then you have to give me a counterexample to say that, okay, look at this example here. It is not true. It makes one statement true, but the other statement false. Can anyone find an example like that? Okay. Well, they are the same. Okay, so you can rewrite, a there exists into a for all if you introduce a negation. Okay. So now we look at the other pair, because when you have this pair, you have a second pair. The second pair starts with this one, which says, it is not true that for all x, p of x is true. Is it really saying the same thing as there exists at least one x such that p of x is false? Think about it one more time, okay? This one says, it is not true that for all x, p of x is true. Is it really saying the same thing as, oh, that means at least there's one x such that p of x is false? Logically, they are the same. Okay? One has the negation on the outside, the other one has the negation in the inside, but then you also have to change the quantifier. The for all quantifier has to be changed to a there exists. So are we doing okay so far with the concept of there exists, which means we can find at least one item, as opposed to for all, which means this applies to everything. Is that okay so far? Just conceptual. Okay, obviously we haven't talked about the application of these things yet. Yep.
Doesn't the first one include multiple things? Like it's going for all of them, but exists is checking for one thing?
There exists is just saying that you can find at least one thing, such that whatever you specify here is true. But itself is a Boolean expression, which means yes, I can find at least one thing, or no, I cannot find at least one thing. So it is not a assertion to say that yes, I'm telling you that there's at least one thing. It is a question of can we find at least one thing. Okay. All right. So now we go into this part here and say that a universal application of for all is very useless, because then you have to say, oh, it means whatever I state has to apply to numbers, has to apply to cars, apply to people, apply to molecules, elements, compounds, and all kinds of stuff. Okay, it's not very useful. So it's really helpful sometimes to say that, okay, let's limit our scope. Okay, so the way we limit our scope is to use implication, and that's why implication is really, really helpful in a class like this. So in this case, we are limiting the context to just say that, you know what, we're only interested in stuff that is in X. If it's not in the set X, we don't care. That's what it's saying. Okay, so let's take a look, let's break this statement apart first and see the components, and then we kind of put it all back together and say, oh, so that's how it works. So let's take a look at this thing first. This is the symbol for implication. And if you remember from the truth table of implication, if the first part of the implication is false, the implication itself is true, without worrying about the second part, right? It is only when the first part is true, then the second part also has to be true in order for the implication itself to be true, right? Okay. So let's just say that p of x has to do with whether a number is a multiple of 2. Okay. So now we can say, oh, we can limit the scope. In other words, we can now start to limit the scope. For instance, I can say x is the set of all integers. Okay? If x is the set of all integers, what about the Miata? What about the MX5?
Doesn't matter.
It doesn't matter. But if E, okay, so when you say for all E, you're also binding E to everything that is possible in everything in the universe, right? So when E is bound to MX5, okay, what happens to the statement itself? Is it true or is it false? In other words, if E is bound to MX5, which is a car, is the inner part, is the implication itself true or false?
Conclusive, right?
It is true. It is conclusive. It is true. Okay. So let's think about what happens when E is a Miata as an MX5, because this part here is saying for everything in the universe. Okay, but I can't really, target one thing when I say for everything. So I'm going to say for each thing in the entire universe, and we'll call that thing E that we are considering. So that process is called binding a variable E, in this case, to a particular thing in the entire universe. So let's say in this particular instance, we bind E to MX5, which is a model of a car. Now we want to evaluate the inside part here and say, is that true or not? And remember, we want X to be the set of all integers, right? So the first question now is, okay, when we look at the implication, we have to evaluate the left-hand side first, okay? So then we evaluate this part here. We say, is MX5 an element of the set of all integers? What do you think? It's not, okay? One would be the set of all the numbers, integers, and the other one is the model of a car, okay? So MX5 is not an element of the set of all integers. If this part is false, what does it do to the entire implication? The entire implication is true. Okay, very good. So there's a meaning to the entire implication, even when E is bound to something that is totally not sensible, or not applicable in this class. Is that okay? Yep.
But couldn't P of X still be false?
Well, you don't even apply that.
Evaluating P of X here.
You don't even evaluate P of X when the first condition is not met.
Yeah.
Because it doesn't really matter. The whole implication is true anyway. Okay, very good. Okay. So now we start to use something. Okay, so in the examples, the set X is basically the set of all the cars ever manufactured. Okay, and P of X is a car lasts forever. So P of X means X lasts forever. So together, what is this statement saying? X is the set of all cars ever manufactured, and the P of X is saying X lasts forever.
All cars last forever.
It means all manufactured cars lasts forever. Okay? Well, is it an assertion saying that is true, or is it a question? It's a question. It's just like X equals Y is a question. It's asking you, are these two things the same or not? Okay. What about this statement here? What is it saying? Keeping X as the set of all manufactured cars and P as X lasts forever. P of X means X lasts forever. So together, this means, in a long way, it means for all E in the entire universe, if E is a car ever manufactured, it implies X does not last forever, because there's a negation before the P. But what is a shorter way to say that? What is the more concise way to say something like that?
No car lasts forever. You said no car lasts forever.
Yep, exactly. It says no car lasts forever. You cannot find me a single car that is going to last forever. Every car does not last forever. That's what it's saying. Now, it can be true, it can be false, okay? But it's what it is trying to state is no car lasts forever. That is the shortest way to describe this statement. All right, very good. So in the end, what we do is, because it is so common that we want to use membership as a filter, because we usually don't want to apply some kind of predicate or some kind of statement to the entire universe. Okay, we usually want to limit our scope to certain things that are of interest to us. So the short form, yep.
I'm wondering why, if the first part of the implication is false, why do we automatically assume it's true instead of false?
Because it's an implication. It is the property of an implication. Okay, so let's switch to the document camera. This is something that we talked about last week, but it's also something that is not easy to, it's easy to understand in a way, but it's also not easy to understand in some other way. So we look at x, which can be false, can be true. We look at y, which can be false or true, false or true. So this is a typical way to start, a truth table of a Boolean operator that involves two independent variables. So now we want to say, okay, what about x implies y? Okay, what is the value of x implies y? So by definition, anytime x is false, the implication itself is true. But when the first part is true, but the second part is false, that is the only time you can say the implication itself is false. And then the last one is true as well. This one relates back to the example that I used in the previous week about what? Yeah, a blue cat being sick, and tomorrow is doomsday, if I remember correctly. Okay, so the third row is the only time you can get a refund, because that's the only row that proves that what I said was false. But what if a blue cat is not sick? What if the first part is not true? Then my statement is true by default. Yep.
What if we assume your statement is false by default?
That is not how the implication operator is defined.
There's no evidence to prove it false. Because there's no evidence to prove it false.
Correct. Yep.
So when x is true and y is false, is it wrong to say x implies itself at that point?
When x is true and y is false?
Yeah.
On the third row?
Yeah.
It means the implication itself is false. And you should get your money back.
Yeah.
Okay? But this is only one way to look at it. The other way to look at this is to look at the other way to define implication. X implies y, and look at implication as an operator, just like plus, minus, and the other operators. This is really the same thing. It is equivalent to not x or y. These two expressions are exactly the same. So that's the other way to look at implication, is not to look at implication using the natural language way of understanding implication, but to use mechanically and say that, oh, implication is defined as as follows. X implies y is defined as not x or y.
Only prove false when x is true, and then we go off what y is
false. Yep. But this makes it more clear why we only have one single row so that the entire application is false. Yep.
So why are we using implication as a filter? Because doesn't that mean the things that we're not checking are included?
So when we use implication as a filter, it means if something is not in the set that we're interested in, then the entire implication is considered true to begin with. Because normally what we want to do is to use a statement like this and to prove it is true. Okay, so you want by default everything else is going to make it true, so that the only thing that can make it false would be things that we are really interested in. Okay, so that's a good point. Thank you. Any other questions about the quantifiers? Both of these are called quantifiers. This is for all. and then there exists is the other quantifier. They're both called quantifiers. We normally use quantifiers in the implicit way on a daily basis. So a lot of times we don't mention the quantifier itself. When we do, we usually use the words every, okay, some. We don't say there exists, okay. So when mom asks you to do dishes, and you answer, and mom insists and go like, okay, when are you gonna do it? Sometime today, right? You don't say there exists a moment in this day that I'll do dishes. You just say sometime, okay, I'm doing my homework, but you're actually playing game.
You know us so well. You say you know us so well.
Well, I'm still like that. What about for all? Okay, when do we use for all in a normal daily conversation? We use every, okay, or all. So tell me one thing that you said today that involves every or all.
Nothing. Nothing.
Nothing is the negation of that, which is good. Okay, so you're basically saying the negation of for all. That means nothing. Okay, but give me an example that you used today, like in your parking experience. A lot of people overuse the universal quantifier, which is for all. So, but what did you say, at least to yourself today, that used the words for all?
There are no clean bowls for cereal.
So for all, so in that case you can say for all bowl negate clean, right? For all bowl X, X is not clean. Yep.
All the parking spots on level 2 of the parking garage are full.
Okay, so for all, X is in parking spot and X is occupied. Okay, very good. So are we okay with this part or not? Are there any additional questions about the for all and there exist? No questions? Okay. So without questions here, we're going to move on. I mean, we're zipping through all the topics. Set theory using quantifiers. So this one is reusing. Okay. There we go. So we're revisiting all of the things that we have talked about before, but this time we use this time we use the quantifiers. So given two things, x and y, how do we know they are the same or not? So the first thing is, well, if they're numbers, we can easily compare, so we don't have to deal with those. So given x and y are sets themselves, then we can say the following. X and y are considered the same if and only if the following is true. Now since x is a set, I can say, hey, let's look at all the elements of x and see if for each element e of x, it should also be an element of y. Is that okay? So let's just focus on the highlighted part here, which by itself is already a statement. And that's why I can apply conjunction with something else. So for all e in x, e is an element of y. That is basically saying what?
Everything that's in x has to be in y.
Exactly. And then the conjunction, the second part says everything in y has to be in x. Well, if everything is in x is in y and everything in y is also in x, the y should be lowercase, by the way, but just look at the y here is a lowercase y because that's what I used earlier. Okay? That is the only time you can say these two sets are the same. Okay? And you can also make it slightly more concise. So the more concise version is for all e in the entire universe. So this time the element of is not applied to e itself on the outside, but instead we use this part here. So consider everything in the entire universe. Okay? But then the first thing we ask is it in x? Well, if it is in x, it has to be in y too. But what if it is not in x? Then it should not be in y either. So it's a more concise way to say exactly the same thing as the one before, It's just rearranged a little bit. Are we doing okay so far? Okay. And then we have the set description, which is basically going back to this notation here, using the bar inside the braces. So when we use this notation, it really means the same thing as this, okay? In other words, before the introduction of quantifiers, this is what we said. The only change is, oh, you know what? We implicitly already used a for all x in the previous case. So let's take a look at this notation again, okay? This is the notation that we normally use when we try to describe membership inside a set. But it really is a short form of this entire thing, which is basically saying, let's consider everything in the entire universe, okay? For everything that is in the entire universe, x is in E if and only if P of x is true. So you can go in both ways now, okay? Because you can evaluate one first, and then you will know what the other side is supposed to be. If something is not in E, what do you know already?
Makes that false.
Make P false, right? What if something is, what if you found something such that P of x is true? It has to be in E, exactly, okay? And this is the power of the if and only if, because it says if one side is true, the other side has to be true. If one side is false, the other side has to be false. So you can go in either direction. You can say, oh, the left-hand side is false. Oh, then the right-hand side has to be false. Or the right-hand side is true, then the left-hand side has to be true. It goes in both directions. What about the empty set? How do we know something is an empty set? Okay, let's spell that out. Okay, so the negation says it is not true that there exists something in the entire universe such that that something is an element of S. It simply says there does not exist anything in the entire universe that is a member of S. S is an empty set. It has nothing. But you can kind of see, how we can apply these things. So by using quantifiers to describe, all those concepts that we have talked about before, I'm trying to help reinforce two things. I'm trying to help reinforce the concept of the set operations, as well as the meaning of the quantifiers. So I'm trying to relate those things, so that you establish more pathways in your head or in your brain to connect all of these concepts. What about intersection and unions? Okay, so this is what we had before. Okay, if you remember, this is what we had before. So it is just implicitly that we are saying, oh, for everything x, okay, for everything in the entire universe, if that thing is in the intersection of A and B, then I know for sure that it is in A and it is also in B. Give me something, it is not in A and in B, I know it is not in the intersection. Okay. So union is about the same, as I said, in the previous portion of the lecture. You're just using a mirror image, okay? Vertically, you're applying the mirror. So intersection becomes union, and all you have to do is to change the conjunction into a disjunction. Say that one more time.
It has to be A or B.
It has to be A or B, which means it can be in. It has to be in at least one of the two sets, but it can be in both. Cartesian product is kind of the same. All we do is to apply the universal quantifier, but this time it is nested. So if I shrink a little bit, just zoom out a little bit, okay. For everything x in A. Then we apply for everything in B, for everything y in B. Then we want to say x, y as a two-tuple has to be an element of a Cartesian product with B. On the other hand, if you give me a two-tuple of any kind in the entire universe, that is, the other way around, give me any two-tuple inside a Cartesian product, then I can tell you for sure that the first component can be found in A, and the second component can be found in B. Now, this conjunction is necessary, because if you don't have this conjunction and you get rid of one part of it, it is no longer true Cartesian product. Let me illustrate what it means, why I said that. So if you only have this part here, okay, without the second part, this part says, okay, find for everything in A, x in A, for everything y in B, xy is an element of the Cartesian product of A cross B. What about something that is not from A or B? Can that be in the Cartesian product under this definition? Yeah, because it won't make this statement false. Are we seeing that? Okay, let me give you an example. Okay, so let's keep that highlight, and then we'll look at an example here. So AB is one set, Cartesian product with 1, 2, which is another set. Okay, so we know the proper definition of Cartesian product means this would have A1, A2, B1, and B2. But I'm going to add one more thing to it. I'm going to add C3. Okay. Now, obviously, this equality is now false. We can no longer say that the two sets, the one on the left-hand side and the one on the right-hand side, are the same. Because where is that C3 coming from? It is not supposed to be a part of the Cartesian product. Okay. But this is based on what we mean, what we understand about the meaning of the Cartesian product. So if I put this right next to this thing here, this condition will still be true, isn't it? Because this condition, the highlighted portion on the whiteboard, on the projector, is simply saying, if I pick anything from the first set and I pick anything from the second set, the two tuple made out of those two components should be a part of the Cartesian product. Hey, nobody says anything about the C3. All it wants to ensure is A1 is in the Cartesian product, A2 is in the Cartesian product. It doesn't say what cannot be in the Cartesian product. Is that okay? And that's why we need the second part. The second part is basically telling us, oh, we also want to put a restriction on the properties of everything that is in the Cartesian product. Okay, so this is an extra constraint. So we go back to look at the example that we have, and this time we can see how this part will become false. Because guess what? C3 is a part of this particular set, right? So we are now saying, oh, C3 is an element of this set here, but is C in A? Is 3 in B? No. So that means this part of the condition is false. So now we know that this set here that has 5 elements is not the Cartesian product of AB first and A and 1, 2. Yep.
But when it says B times X exists A or Y exists B?
Say that one more time.
It's B parenthesis X exists A. At the end, there's no. I don't understand why there's parentheses.
Are you talking about this portion or this portion? The left?
Second, the end.
The end here?
No. To the left. To the B. Yeah, right there. After that.
Mm-hmm.
Why is there parentheses? Like it's saying that the tuple exists in A cross B, and then what is the rest?
Okay, so for all xy as an element in the Cartesian product of A and B, this has to be true. X in A and B, Y in B is a conjunction that has to be true given xy as a two tuple is in the Cartesian product. This is how we define Cartesian product. So when you have A, B, as individual sets, then the Cartesian product has to meet this requirement. This entire thing has to be true for A cross B. for A Cartesian product with B. Okay, well, we are running out of time today, so I forgot to pass the row sheet again. I would just say that we are, for the most part, here. All right, so on Wednesday, what we'll do is we'll finish up the discussion of this entire slide. We are already at the end of this already. I will post the notes on functions. I got most of it written already. I just need to put a link on the website. So I will post the link and make an announcement. Do you guys get an email message or some kind of messaging once I post something with the announcements?
I've been getting those.
You do? Okay, great.
Yeah.
Okay. Okay. So I'm going to post a notification when I have a link, to the new material.
You can say